Hello, and we are all stuck at home with trying to avoid the coronavirus. So your lectures are going to be, they're going to be by video. So hello, all my math peoples. Today, I'm actually going to go over something that we went over in class already before, but this seemed like a good test video, and if no other reason, then you've already received this information. So today we're going to go over the eigenvector eigenvalue problem. Let's talk about some required skills here. Okay, so throughout these problems we're going to work, we'll need a few prerequisite skills. We need to be able to take the determinant of a matrix. Okay. We need to be able to find the roots of a polynomial. You'll remember that from some of your algebra classes. Okay. And we need to be able to solve homogeneous systems. The method really doesn't matter, but it's most efficient since we're dealing with a matrix already. If we use Gaussian elimination. Okay. All right. So with these things in mind, let's go ahead and take a look at what the eigenvector eigenvalue problem actually is. And at first glance, it seems a bit random. Suppose I have some arbitrary matrix A. Okay, it's nothing really special about this matrix, but for our purposes, it will require it to be square matrix since we're going to want to take a determinant later. So we have some matrix A, and I will left multiply A times vector V, and I'd like the result to be. Well, I'd like the result to be equivalent to some scalar lambda times v, and that's very odd, right? Because if I multiply this matrix times a vector, I'll get another vector, and there's no reason that vector would be a scalar multiple of the original vector. But we'd like to solve for all of the possible values, which do make this work. Okay. Now I know what you're thinking. That doesn't have a whole lot to grab a hold of, right? There's not a lot of here, but let's use some algebra and we'll rearrange this a little bit, see if we can't get a better handle on this. So let me go ahead and I'll subtract lambda v. Okay. All right, so now I have AV minus lambda times v is equal to 0 vector, and I know you want to factor out that v because that seems perfectly logical. The problem with doing that is a minus lambda wouldn't be well defined at that point in time. Lambda being a scalar and a being a matrix, we're not exactly sure how to subtract a matrix from a scalar, but we can, this is a trick that's used in linear algebra a lot, we can insert an identity matrix in here, okay? Because of course, since it's the identity matrix, we know that I sub n times v is of course still v, so I can replace v with I sub n times v, and at this point in time, now I can factor, okay? So now I have a minus lambda I times v is equal to my 0 vector, okay? And this is of course well defined. Both of these are n by n matrices. The subtraction is fine. So now we've seen something like this before though, okay? We have seen a matrix times v is equal to 0. If I just hypothetically assume that a minus lambda I is b for the moment. Okay, so I don't even know if you guys can see that. That may be a little bit too light. Okay, so we're just going to assume that that's b for the moment. Then this actually reads b times v equals 0. Where have we seen this before? We've seen this in our invertible matrix theory, right? Now we know this has a solution, right? We know there's a vector v for which is a solution. There's the trivial solution. V could just be the 0 vector. And then b times the 0 vector would of course have to be 0. But we're not interested in that one. We're interested in the non-trivial solutions. So I want non-trivial solutions. That means I want more than one solution. And the invertible matrix theorem has a line that says B times V is equal to 0 has only the trivial solution V equals 0 if B is invertible. But I want V not to be invertible. That'll give me more than just the trivial solution. So again, sort of following the logic here, okay, we want many solutions. Okay, and in order to have many solutions, I need B to not be invertible. Okay, all right, that doesn't help an incredible amount, but the invertible matrix theorem has lots of equivalent things to this being non-invertible. One of which is, again, think determinants, think of our required skills. One of which is the determinant of B is equal to 0. That's the contrapositive, actually. The invertible matrix theorem says that if B were invertible, the determinant would be a non-zero, and that goes both ways. And so if I have my determinant of B equal to 0, then I know that it's not invertible, and then I'll know this has many solutions. So again, putting this together, what are we looking for? I know that these values of lambda and V, which create this eigenvector, eigenvalue problem solution, are going to occur when the determinant of A minus lambda I, okay, so the determinant of A minus lambda I is equal to 0. This is what we're really looking for, right? Yeah. So this fact here, this is going to give me all of the solutions to this eigenvector, eigenvalue problem, right? Okay. All right. I'm not going to go through the theory part just now. I want to work a few examples. We'll work those, and I'll sort of talk about the possibilities of what can come up, what can arise whenever we start looking at problems of this nature. Okay. All right. So I've got a few matrices planned out for us here. Don't worry, I picked the fun ones. Okay. You know me. I always pick the fun ones. Okay. Let's start with this one. So we've got A here. Okay. All right. Here we go. Let's see. 3, -1, 0, 0, 2, 0, -1, 1, 2. Now, here's my matrix. Again, I want to find the eigenvectors and eigenvalues for A. Now I'm going to do something once, and once only. Technically, I don't actually want A. If you remember, the fact we were looking at is, actually what we want is we want the determinant, not of A, but of A minus lambda I. In this particular case, it's I sub n, but in this case, it's I3. Okay. I'm going to work out what A minus lambda I is, and then I'm also going to talk about why we never ever have to work that out ever again, right? So we really should just skip straight to taking this determinant, but again, this one time I'm going to work it out, and then I'm going to erase the work, so we'll handle that in a second. So let's talk about what A. So A minus lambda I. In this particular case, it's I3. Okay, so this would be, let's see, what's A? A is 3, -1, 0, 0, 2, 0. -1, 1, 2. Okay, so minus. Lambda is just some scalar here. And I3, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so now I need to multiply this scalar in, and if we remember back to our matrix operations, multiplying a scalar times a matrix, I just take the scalar and distribute it to every single quantity in that matrix, right? Now, of course, lambda times 0 is going to give me 0. So in reality, the only actual change being made here is that instead of having 1s on my diagonal, I'll have lambdas. That's it. Okay. At which point in time, I just have one more operation to finish this off. But again, when I subtract matrices, these are subtracted component-wise. Everything that's not a diagonal, like this entry here, that'll be -1 minus 0, those aren't going to change. 1 minus 0s won't change. The only actual change occurs on the diagonal entries, where the diagonal entries will have lambda subtracted from them. So I've got negative 3 minus lambda, negative 1, 0, 0, 2 minus lambda, 0, negative 1, 1, and 2 minus lambda. And if we think about it, all of these things were independent of my choice of A. In reality, what's going to happen for us every single time is that really A minus lambda I is just going to subtract a lambda from each diagonal entry. Yeah. So we don't actually want to have to work this out every single time, right? This seems reasonable enough that we can just shortcut this all the way to just taking a determinant of A minus lambda I. So let's go ahead and do that now. Okay, so let's see. All right, so I'll look at my determinant. Okay, I'll go ahead and subtract lambda from each of my diagonal entries. So there we go. So 3 minus lambda, negative 1, 0, 0. 2 minus lambda, 0, negative 1, 1, and 2 minus lambda. Okay, so we'll go ahead and take a determinant here. We'll go ahead and expand this by the second row. It's got a bunch of zeros in it. Oh, I guess technically I could use the third column, but I don't know, I'm kind of partial to rows. Okay, so let's see, we'll take out the value itself, that's 2 minus lambda. Times the permutation sign for this particular entry, that's the 2, 2 entry, that's even. Okay, so it's a positive 1. And times the remaining determinant when I ignore, of course, that row and column. So let's see, that gives me, okay, 3 minus lambda, 0, and negative 1, and 2 minus lambda. Okay. And this turns out to be, well, a very nice polynomial. Okay. So I've got 2 minus lambda times 3 minus lambda times 2 minus lambda. Okay. That's nice, right? So, will they always come out this nice? No. Will they always come out to be a polynomial? Yes. Hence the requisite skill, you being able to find the roots of a polynomial. Because remember, I care about when this thing is equal to 0, right? Now, side note, this polynomial has a, well, we have a special name for it. Our matrix here is A, and we'll refer to this as the characteristic polynomial of A, right? The characteristic polynomial of A. And in general, I don't care necessarily about the polynomial itself. For this particular problem, I care where it equals 0. But I should point out that this matrix is not unique for having this particular characteristic polynomial. Several matrices will have the same characteristic polynomial. This is not a one-to-one correlation. Okay, but that's okay. We care where this specifically is equal to 0, so the roots of this polynomial. And here this came out factored for us. It's very nice. We can go ahead and see that lambda equals 2, lambda equals 3, and lambda equals 2 again. These are the actual values. And these are called the eigenvalues of A. Okay? Now I'm going to label them with some subscripts. And you'll notice that I do have a particular root which has occurred more than once. That can happen. Okay? It's got the root 2 here has a multiplicity of 2. I got it 2 times. And we'll tackle that one second. Let me handle 3 first. Okay? So again, supposedly this is a solution for the determinant of A minus lambda I is equal to 0. But again, remember, the motivation here was A times some vector is equal to lambda times that vector, right? And what this is telling me is that there's some non-trivial solution V where A is this matrix and lambda is 3, right? Or lambda is 2. We'll get to that one in a bit. Okay. Well, yeah, but what vector? Let's find out. Okay. So here's how we find the eigenvectors, the associated eigenvectors for each eigenvalue. Okay. I don't have a very large board here, so we're going to go ahead and sort of break these apart. We'll do 3 first, and we'll do 2 second. Okay. So let's see. Let's talk about 3. Okay, I'm going to call 3, and we'll call that lambda 1. Okay, so there's my first eigenvalue, lambda 1. And if I'm looking at this, remember this is a minus lambda I times v equals 0. If you remember from our proof earlier, okay, we had this particular line. We had a minus lambda I is equal to 0. And we can actually use that now that we have lambda. Now that we have lambda, this should be a minus 3i for this particular lambda. And I know, again, that's just subtracted this from my diagonals. So what we need to do, actually, is we need to just plug in 3 here, which of course would just subtract this from our diagonals. Let's go ahead and do that. Let's see, that gives me the matrix A minus lambda I is, well, it's 0, negative 1, 0, 0, negative 1, 0, negative 1, 1, and negative 1. And again, just to get from here to here, it's a minus lambda I, lambda here is 3. I subtracted 3 from each of my diagonal entries. And so what I have is I have this times v is equal to 0, but this is just a system, right? This is the matrix form of a homogeneous system, right? Yeah, we know how to solve these. This was given earlier in the semester. We can solve these by, again, making an augmented representative matrix. We'll call that A pound. Okay. Well, I don't want to use A because I have A here. We'll call it B pound. Okay. Okay. So B pound, which is equal to. There we go. So this matrix again, and my solution column, the 0 vector here, would be 3 by 1. So I need 3 zeros. So that's 0, negative 1, 0, and a 0 for the solution column. 0, negative 1, 0, and a 0 for the solution column. And I have negative 1, 1, negative 1, and of course a 0 for the solution column. Okay. We can solve this using Gaussian elimination. We'll go ahead and put this in row echelon form. Several ways to do this. We'll make it look nice. We'll do P13 first. That leads me to negative 1, 1, negative 1, 0, 0, negative 1, 0, 0, 0, negative 1. Okay. And I'll go ahead and multiply row 1 by negative 1. And I'll multiply row 2 by negative 1. It's going to make some nice ones for me. Okay. Here we go. So I have 1, negative 1, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0. And we can just finish this off with, if I add a negative 1 multiple of row 2 to row 3, that'll go ahead and put me into my row echelon form. So A2, 3, negative 1, okay, which gives me this, okay. So here's my matrix here. So I've got 1, negative 1, 1, 0, 0, 1, 0, 0, and of course 0, 0, 0. Now you'll note I have a row of all zeros at the end of this, right? Implying I'm going to have infinitely many solutions, which of course we needed. Yes? If there was a unique solution, I would know what it is already because v equals 0 is a solution. Okay? All right, fantastic. Well, I'm going to solve this. I'm going to go ahead and parameterize one of my variables here. I need a little bit more room. Okay. Let me go ahead and parameterize. Let's call these variables. I'll call these, let's see, x1, x2, x3. It's a bit lazy because I named my vector v, but it's fine. Okay. So let's see. I'm going to go ahead and parameterize. Let's let x3 equal to t. And we'll go ahead and look at my second line here. That corresponds to an equation. 0 times x1 plus 1 times x2 plus 0 times x3 equals 0. But, I mean, actually that just reads x2 is equal to 0, doesn't it? 1 times x2 is equal to 0. Okay. My top line then, of course, corresponds to the equation x1, 1 times x1, minus x2 plus x3 is equal to 0. But x2 is 0, x3 is t. So x1 plus t equals 0, and so of course x1 is equal to negative t. Now, this tells me that every possible solution to this particular system is of the form negative t, comma, 0, comma, t, and for us, t is some real number. Okay. Now, of course, again, this includes the 0 vector. We did mention the 0 vector is, in fact, a solution. Together, all of these vectors, they form a space. They form a vector space. Okay. Specifically, these are called the eigenspace. This is the eigenspace for this particular value. And what we really want is we just want to pick one of those vectors to serve as a basis for this one-dimensional eigenspace. You can choose any value of t you'd like apart from 0. We typically choose whatever makes the numbers look nicest. Okay. I'm going to pick 1, right? So if I pick 1, if I pick t equals 1, then what I get is I get the vector negative 1, 0, 1 as a representative eigenvector here. Now I'm going to name this one v1, eigenvector 1, so v1, just because it corresponds to lambda 1 here. So v1, so I've got my eigenvalue and my corresponding eigenvector. And of course, any scalar multiple of this is also an eigenvector, but this is just the representative one. Okay? And this is fine. This is going to happen anytime you have a root for this characteristic polynomial which has multiplicity 1. You will always get one exact eigenvector. In point of fact, for every root you get for this characteristic polynomial, you have to get at least one eigenvector. But what if you have a multiplicity larger than 1? Well, fortunately, this particular problem gave us another eigenvalue. Okay? If you remember, that eigenvalue had multiplicity 2 when we found the roots of this characteristic polynomial. We had 3, and we got 2. We got 2 twice. Okay? So let me go ahead and label here lambda 2. That was my second eigenvalue, if you remember. And I'd like to find some eigenvectors for this. Now, I know I'm going to get 1. I have to get 1. But I might get more. And it turns out that you can always get up to the multiplicity of the root. Linearly independent eigenvectors. Okay? So I might get 2 here. Since I had multiplicity 2, I might get 2 eigenvectors. I might not. I might only get 1. Let's see. Again, plugging this in again, we care about where a minus lambda I times v is equal to 0. So again, we're going to subtract lambda from each one of my diagonal entries here. That's going to leave me with the following matrix. Okay, so a minus lambda 2 I, that matrix is, see, 3 is 1, negative 1, 0, 0, 0, 0, that's nice. Negative 1, 1, 0. Okay. And again, this is part of the homogeneous system. A minus lambda I times v equals 0. So we're going to do the exact same thing we did last time. We'll treat this as a homogeneous system. We're going to make an augmented representative matrix here. Okay. Again, we'll just call this B pound, just because, again, I don't want to get my letters all mixed up. And that's just 1, negative 1, 0, another 0 for the solution. Here we go, 0, 0, 0, 0 for the solution, and negative 1, 1, 0, 0 for the solution. This actually goes into row echelon form very easily, really quickly, just one operation here. We'll do A1, 3, 1, okay, and row 1 is a negative 1 multiple there, so that gives me this following matrix. Okay, so also needs to be parameterized. Again, if you don't get a row of all zeros, then you're not going to get more than one solution, more than the trivial solution, and that's a problem, right? You have to get a non-trivial solution. So let's see. I'll go ahead and parameterize. Here we go. Let's say x2 is equal to s, x3 is equal to t. And let's see, this top equation then reads 1 times x1 minus x2 plus 0 times x3 is equal to 0. But x2 is s, so that's x1 is equal to s as well. Okay? So this tells me that every possible solution to this particular equation when lambda is 2 is of the form s comma t, where s and t are both real numbers. Again, this forms a space, forms a vector space. This is the eigenspace for this particular eigenvalue. And we'd like a basis, right? So we'd like a basis. Now, it's important to look at this. I've got two independent choices here for s and t. This is a two-dimensional space then. As such, I'm going to need two linearly independent vectors to create a basis for this space. And I can achieve that just by selecting each variable in turn to be 1 and the remaining ones to be 0. So again, to get a first vector, let me go ahead and let s be 1 and t be 0. Okay? And if this happens, then I get the vector 1, 1, 0. And then of course I could let s be 0 and t be 1, which would of course give me the vector 0, 0, 1. These two vectors are linearly independent. They're both members of this two-dimensional vector space. So it turns out that lambda equals 2 actually has two eigenvectors. It's kind of two-dimensional eigenspace. Now, I'll label these again with just subsequent subscripts here. We'll call this one v21, again corresponding to lambda 2. This will be the first vector. I'm writing these vertically, and I'm not going to lie to you, I don't know why. Eigenvectors tend to be written vertically. There's probably a good reason for it. Okay. All right, yeah. All right, so all that work, and what do we have? Well, what we have is for matrix A, we have, let's see, we've got two distinct eigenvalues, 3 and 2. We've got 3 eigenvectors corresponding to those eigenvalues. And everything went fine here, but what could have gone wrong? Well, I mentioned you had to get at least one eigenvector for each of these eigenvalues, and you do. But what if you got less than the multiplicity? You see, if 2 only had one eigenvector here, if it didn't have one, that could have happened. That's a reasonable thing that can occur. But we have a term for this, right? So you'll note that this is an n by n matrix. Okay, so A is n by n. Okay, okay. If A has n linearly independent eigenvectors, then A is non-defective. Okay, so we call it non. So this is a non-defective matrix. It's 3 by 3. I've got 1, 2, 3 linearly independent eigenvectors. This is non-defective. Okay. However, I could have gotten less. Okay, I could have gotten less. If I do get less. Okay, so again, so if A has less than n linearly independent eigenvectors, my penmanship gets bad the further it gets away from my body. Eigenvectors, then A is said to be, obviously, if it's not non-defective, it would be called, well, defective. Okay? All right, fantastic. This is fine. Okay? Yeah? This is not terrible. Now, actually, I want to do a couple more examples because if we can sort of troubleshoot this, where might problems occur? Well, we're going to end up with a polynomial, right? And we need to find the roots of that polynomial. Now, well, these roots came out nice. Might the roots come out ugly? Yeah, honestly, yeah. The roots might come out. Terrible. So, what do we do? Well, if the roots come out complex, that's actually not that bad. Think about if I were to get, so again, I had a polynomial which did not have complex coefficients, okay? And what I came out with was I apologize, I keep walking off camera because my computer screen keeps shutting off. I need to fix the idle. Sorry, should have thought about that before I was recording. But if I come out with a complex value for my eigenvalue, let's say lambda is 1 plus 3i, right? So a plus bi. Well, because it came from a polynomial which didn't have complex coefficients, I know that the conjugate a minus bi is also a root of that polynomial, which of course means that it would also have to be an eigenvalue, okay? Well, that's fantastic, actually. And what would be even more fantastic is if somehow the eigenvectors related to those eigenvalues were also related to one another, and it turns out they are. Okay, so a fantastic theorem states that for conjugate eigenvectors, you have, for conjugate eigenvalues, you'll have conjugate eigenvectors. So we can actually save ourselves the trouble. As it turns out, it's a little bit easier if you come out with a complex root because you don't have to do both of them, you just do one of them. Okay, that seems fantastic. Okay. Again, let me work a couple more examples here, just sort of wrap this up. And we'll let it go there. I got a couple more, just because I want to be able to show you some of the things that might happen. Okay, I will go ahead and tell you that most of the time the mistakes made from students with this type of problem, they don't come specifically from the methodology itself. This is not incredibly complex. You just uses skills that you've used before in your math classes. What happens is inaccuracies. Students will they'll get lost in the details. If you make a small arithmetic mistake earlier on, your polynomial turns out wrong, your roots will turn out wrong, and everything just sort of turns into a mess. So please make sure that you're being very, very careful, very precise. Okay. Remember, you work consistently because consistency breeds accuracy. Right. Okay. So let's try another one here. Let me go ahead and label, okay. Let's call this matrix C. Try and maintain some different labels for things as I'm working through these videos. Let's see, I've got 9, 37. So you know something's going to be up to this problem when you pull it out of the book and there's got a 37 in it. Like, why would you use a 37, right? Okay, here we go. So -1, -3, okay? Okay, fair enough. So let's see. Find eigenvectors and eigenvalues. So find all eigenvectors and eigenvalues. Fine. Okay, so again, what I really want is I want the determinant of, in this particular case, c minus lambda I. Fine. So let's see. That's 9 minus lambda, 37, -1. -3 minus lambda. This is a very nice 2x2 matrix. We can just, of course, do the determinant here. This is 9 minus lambda times -3 minus lambda minus -1 times 37. Sure. This gives me lambda squared minus 6 lambda minus 27 plus 37. So lambda squared minus 6 lambda plus 10. Okay? Sure. Fine. This doesn't factor. So, well, it's not that bad. Okay? We can easily find roots. Okay? We know how to do this. Let's do some scratch work here on the side. We've got, let's see. Lambda is equal to, okay, it's just standard quadratic formula. So 6 plus or minus the square root of 6 squared minus 4 times 1 times 10, all divided by 2 times 1. So lambda is equal to 6 plus or minus the square root of negative 4 over 2, which gives us complex values, right? This gives me 3 plus or minus I. Okay? Okay, so I've got 2 eigenvalues. And again, they're complex, but that's okay because they're conjugates. Okay? So let me go ahead and write down my eigenvalues here. I know I'm call lambda 1 3 plus I because, I don't know, it had the plus sign. Okay? And lambda 2, 3 minus I. Okay, fantastic. Okay? And again, remember, I don't have to do both of these, right? Because they're complex conjugates, I know that the eigenvectors associated with them, I'm guaranteed to get at least one for each, are going to be conjugates as well, right? Let's do that now. Okay, so let's see. Okay, so we'll just take lambda 1 here. Okay, again, the associated system, I want C minus lambda times I. Take this value, subtract it from my diagonal entries here. Okay, so let's see. That gives me, okay, so C minus lambda I in this particular case is, here we go, see 9 minus 3 plus I, 37. I've got negative 1, and then I've got negative 3 minus 3 plus I. Okay, and remember, I care about this times a vector is equal to 0. This just corresponds to creating an augmented representative matrix here, which we're going to call, I don't know, I'm not going to give it a label. Okay. All right, so here we go. Go ahead and subtract, and I get 6 minus I, 37, negative 1, and this is negative 6 minus I. All right, fantastic. And let's see. All right, let me just put my solution column on here. Here we go, 0, 0. Okay, go ahead and use our Gaussian elimination. Let me go ahead and permute 1 and 2, and negative 1, negative 6 minus I, 0, 6 minus I, 37, 0. Fantastic. Okay. Fair enough. Let me go ahead and eliminate this bottom row here. Okay, I mean, I know it's got to come out to all zeros, right? We were going to multiply, we will add, let's see, a 6 minus I multiple of row 1 to row 2. This is negative 1 times 6 minus I plus 6 minus I. It's got to give me 0. Those are additive inverses. So let's see. Okay. All right, first row won't change. I've got negative 1, negative 6 minus I, 0. Second row, that's a 0. You can verify for yourself. 6 minus I times 6 minus I, that's 6 minus I squared, that's 36. So negative 6 minus I times 6 minus I, that's negative 36 minus 1, that's negative 37. Negative 37 plus 37, 0. Fantastic. Okay, great. All right, parameterization. Yay. Here we go. Second value, I'll go ahead and let that one be t, just because. Okay. My first equation then reads negative x1 plus negative 6 minus I x2 is equal to 0. Okay. Plugging in t for x2, I get x1 is equal to negative 6 minus I t. Okay? All right, fair enough. Okay. Again, I know then all the solutions to this particular equation are of the form negative 6 minus I t, comma, t, T itself is a real number for us. Okay. And let's see. Pick anything you want. I don't know. No reason not to pick 1. Okay. So let's see. All right. Choosing 1 gives me the eigenvector -6 minus I 1. Okay. And again, I don't have to do the second one. Okay. These eigenvalues are conjugates, so the eigenvectors, I know those also are going to be conjugates. Okay, a little bit more space for this one. Okay, so lambda 2, 3 minus I, so V2. Okay, this one's going to be, what conjugate of -6 plus I is, sorry, minus I is -6 plus I. The conjugate of 1 is 1. Yep, 1 plus 0I, 1 minus 0I. Okay. Yeah. This one's really quick and easy, right? Shouldn't be afraid of complex. Don't be afraid of complex numbers. Complex numbers are your friends, right? Cut the work in half. We like those. Okay? It's fine? All right, fantastic. Let me work one more. Okay, one more just so that we can see one more aspect of this. I don't want to do too much more here. Otherwise, I'm probably losing you. Probably pause the video at this point in time to get a snack or something. That's okay. I'm kind of hungry myself. Anyway, so let's see. Let's do one last example. We've got, what do we have? We've got -1, 1, -1, 3. Okay. Again, let me go ahead and find all eigenvalues and eigenvectors. Okay, fair enough. Again, what determinant? A minus lambda I. Here we go. -1 minus lambda. 1, -1. 3 minus lambda. All right, determinant. That's -1 minus lambda times 3 minus lambda minus -1 times 1. Okay, this gives me lambda squared minus 2 lambda minus 3 plus 1, or lambda squared minus 2 lambda minus 2. Okay. Oh, all right, let's see. All right, again, I'd like to find some values here. Okay. This does not factor. So I get lambda is equal to, let's see, 2 plus or minus square root -2 squared minus 4 times 1 times -2. Okay, all divided by 2 times 1. Lambda is equal to 2 plus or minus the square root of, this is 4 plus 8, it's 12 over 2. Lambda is equal to 1 plus or minus square root of 3. Okay. Again, not complex, right? Not complex. Okay. Okay. Fair enough. Again, solving for the eigenvectors shouldn't be that bad, right? Okay. So let's see. Let me go ahead and write down my eigenvalues here. Lambda 1, 1 plus square root of 3, and lambda 2, 1 minus square root of 3. Okay, let's see what happens. Let's see what happens whenever we find our eigenvectors here. Okay. Okay, so let's see. A minus lambda I. Again, I'll start shortcutting some of these steps. I'm going to want the augmented matrix for A minus lambda I for each lambda. Okay, so I've got -1 minus 1 plus square root of 3. That's -2 minus square root of 3, and then 1. negative 1. Again, subtract this from each diagonal value. So that's 3 minus 1 plus square root of 3. That was 2 minus square root of 3. Let me give my solution column here. Got some zeros. Okay. All right, let me go ahead and I'm going to go ahead and multiply row 2 by negative 1. This is unnecessary, but I just want that to be a positive 1. Okay. And after that, I'm going to go ahead and permute rows 1 and 2. So I've got 1, negative 2 plus square root of 3 equals 0. And here I've got negative 2 minus square root of 3 and a 1 equals 0. Ugh. 0. It is my solution column, but we're not going to stick little signs in there. It's ridiculous. Okay, so, and again, using this one to annihilate the value below it, go ahead and use A12. Let's use 2 plus square root of 3. Of course, that's the additive inverse here. Let's see what we get. First row, no changes, right? So negative 2 plus square root of 3. Second row, that'll give me 0. And now I need to take negative 2 plus square root of 3, multiply it times 2 plus square root of 3, and add that to 1. But what you'll find when you multiply these two things together is that negative 2 plus square root of 3 and 2 plus square root of 3 equals negative 1, right? Now, I know that seems weird that it would line up that way, but remember, if this process doesn't have a row of all zeros, then it won't have non-trivial solutions, and I have to have a non-trivial solution. I knew this was going to be 0 to start with, yeah? And the numbers might look weird, but we can sort of anticipate some of the results here. Okay. Well, let's see what we get from the parameterization. Okay. Let me go ahead and let x2 equal t. My first equation here then reads 1 times x1 plus negative 2 plus square root of 3 x2 is equal to 0. X2 is t, so this just becomes x1 is equal to, again, subtraction, so that's 2 minus square root of 3 t. And again, everything of this particular form is an eigenvector, specifically 2 minus square root of 3 t comma t, where t is, again, for us, some real number. We'll use our real number scalars unless otherwise stated. And I can pick any value for t to pick one vector out of this to serve as a representative for this particular eigenspace. I'll pick 1 just, because. Okay. So v1 is then, let's see, 2 minus square root of 3 and 1. Okay, now, I'm going to go ahead and do lambda 2, but what do you think it's going to come out to? So just take a second, maybe think in your brain, what do you think it's going to come out to? I mean, these are not technically complex numbers, right? Yeah? So these are not complex conjugates, but aren't they conjugates? I kind of feel like they are. Let's do lambda 2. Let's do lambda 2 just to verify that this very nice rule that happens when I have conjugate polynomial roots for my characteristic polynomial giving me these conjugate eigenvectors, just to make sure that works, right? Always going to verify. All right, so let's do lambda 2. Again, a minus lambda I. We'll set that one up just like we did previously. Subtract this value from each of your diagonal values. A negative 1 minus 1 minus square root of 3 gives me negative 2 plus square root of 3. That's a 1. Negative 1. And I have 3 minus 1 minus square root of 3. That gives me 2 plus square root of 3. And okay, here we go. 0, 0. These operations should look very similar, giving me very similar results. Again, go ahead and add A12. In this particular case, I want the additive inverse of negative 2 plus square root of 3. That would be 2 minus square root of 3. Okay, again, row 1 doesn't change. I'll let you do the arithmetic here, but again, we can anticipate this is going to come out to a row of all zeros. And what I notice then is what? What I notice is that let's let x2 equal to t. So I've got 1 times x1 plus negative 2 minus square root of 3 t is equal to 0. There's my top equation. And again, solving, I just get x1 is equal to 2 plus square root of 3 t. And again, anything of this type giving me a solution in my eigenspace. So of course, everything of the form 2 plus square root of 3 t comma t, where t is some real number. Any of these things are in the eigenspace for this eigenvector. I'll pick anything I want. I'll pick t equals 1 just because. Okay, it's nice. It illustrates the point nicely. And look at what the second eigenvector came out to be. Came out to be 2 plus square root of 3, 1. Again, the conjugate. So I should note that the rational numbers function just fine as a field. And I won't get into it in this lecture, but you can extend fields, okay, by adding in various other algebraic solutions, okay? So the complex numbers are an extension field of the real numbers, right? You add in I. Well, it turns out you can add in 3, right? Any one of these things you add in as an extension field tends to be the root of some polynomial. Specifically, square root of 3 is the root of the polynomial x squared minus 3. Okay? These things, while we don't typically refer to them as conjugates, are conjugates. Okay? Really, when we say conjugate, we tend to refer to the complex conjugate. We sort of shorten it to conjugate, but this applies as well, right? So these values, square root of 3, they create this extension field, and so you'll get the same property that if you end up getting conjugate, okay, conjugate eigenvalues, you get conjugate eigenvectors. Okay, and I cannot emphasize enough. That's true because our characteristic polynomial, the polynomial for which we're finding roots, all of the coefficients are in fact rational numbers, right? So because all of our coefficients are rational numbers, these nice conjugate rules apply. All right, guys. Hopefully at this point in time, you should be able to take any matrix, and if your algebra is good enough, you should be able to find all of the eigenvalues and eigenvectors for that matrix. You should be able to tell yourself whether or not the matrix is either defective or non-defective at the end. Okay? In our next video, we'll talk about one of the things that we actually use these eigenvectors and eigenvalues for. I should point out they're used for a lot of different things. Okay? But we are very specifically going to use them for something called diagonalization. Okay? And so good luck. Your homework will be posted online if I didn't give it to you already. I may have. I don't know. The coronavirus. I don't have it, but you know, it's kind of driving me nuts. But yeah, good luck, guys.